Hello, my name is Carson Jameson, and I will be doing my reading summary 4 paper on LunaNet. So within the next decade, NASA is planning on new lunar missions involving astronauts on the moon under the new Artemis program, which is a successor to the Apollo program back in the 20th century. With this will come, of course, problems for astronauts on the moon, as they will have the need for properless wireless communication between astronaut users on the moon and on other users on Earth. Proper transmission of scientific data will also be incredibly important, since lunar missions will be constantly updating their progress on very constantly. Astronauts will also need space weather updates in order to prevent them from the exposure to harmful solar radiation, since the moon doesn't have an effective atmosphere to protect astronauts from this said radiation. So LunaNet is unique to approaching these problems, as it seeks to enable more dynamic and network-centric operations, compared to more traditional approaches which seek link-centric space communications and navigation. There are also other similar approaches to LunaNet, such as MARS, which stands for Multi-Attribute Routing and Scheduling Algorithm, and was proposed in 2020. And it seeks to find the optimal scheduling in messages between various nodes. There is also cluster-based architecture, which was proposed in 2017, and it seeks to fix the problem of dynamic coupling among divided subnets and reduce overall data congestion. Other related approaches in designing an interplanetary network can be seen from the works of TP Planet, which seeks to address the problem of poor performance of TCP in an interplanetary network. Nokia has also been selected by NASA quite recently to construct the first cellular network on the moon, which hopefully in the near future can be used alongside LunaNet. So the main goal of LunaNet is to implement a reliable and flexible network infrastructure for lunar mission operations. In order for this to be achieved is by the use of an overlay network known as delay-tolerant networking. Delay-tolerant networking is useful for networks that have nodes with extremely large distances between them, such as satellites orbiting the Earth and the Moon. Delay-tolerant networking uses an approach known as store and forward, where data is incrementally moved and stored in nodes across the network. Most often, data is stored in bundles, which are usually chunks of data with pretty large sizes, and this is transmitted via the bundle protocol throughout the network. The infrastructure of LunaNet provides 3 main services, which is implemented to meet the needs of astronauts during lunar missions. So the first set of services is the networking services, which allow addressable and routable data units to be transferred between nodes in either a single link or over a multi-node end-to-end path. These services allow users to communicate with one another over the network. The second set of services is the position, navigation, and timing services, which allows users to get information on their current location, their current velocity if they are in orbit or operating a wheeled vehicle on the moon, as well as synchronization for the current time. This set of services also provides search and rescue location services for astronauts in distress. The third set of services is the Science Utilization Service, which provides tools for efficient methods of data collection and transmission across network nodes. This set of services also provides astronauts with updates on solar weather, as to protect them from unexpected solar events involving high amounts of harmful radiation. So one key feature of LunaNet is that it is incredibly flexible and many different types of infrastructures of the network can be implemented. For example, in case A, it shows that an instance of the network where each lunar orbiter has a trunk link with Earth. This approach is not the most effective method, as it requires the need for multiple assets on Earth to communicate with each relay. For case B, lunar orbiters have crosslinks with one another, which allows for a single orbiter to communicate with Earth. However, this infrastructure requires crosslinks at full aggregate data rates. Case C shows a relay in high lunar orbit, which can receive multiple links from lunar orbiters. These relays may usually be in the form of larger spacecraft. Case D shows a relay on the lunar surface, which receives multiple links from lunar orbiters. Lunar surface relays would not provide the same amount of contact time for each lunar orbiter as high lunar orbiter relays would. Thus, case C may be the best infrastructure to choose from. So as a proposed solution for lunar mission communications, LunaNet provides some advantages. The first advantage, as mentioned earlier, is that it is incredibly simple in terms of overall design, and with this design, it can provide some very useful services that will be able to help astronauts during lunar mission operations. Also mentioned in earlier slides, the next advantage is that the architecture is incredibly flexible and can be implemented in a number of ways to ensure optimal transmission rates between nodes. The last advantage is that security remains a high point of interest in the design of LunaNet, since scientific data should remain confidential among lunar researchers, and it would be a hazard for astronauts if malicious users were to overload the network. Thus, security architecture will be implemented as part of LunaNet. So LunaNet, however, does suffer from disadvantages, such as the ones listed on this slide. The first disadvantage of LunaNet is that since it uses delay-tolerant networking, then transmission speeds between nodes are most likely going to be slower than conventional networks. Another disadvantage is that LunaNet is currently only designed for research and very specific economic purposes. So therefore, the average terrestrial user will most likely not have access to the network. One final disadvantage is that since the deployment of the network will involve space transportation via space rocket ships, then the deployment of the network is most likely going to be very costly, probably in the area of billions of dollars. So finally, I have a list of possible improvements for both the study as well as for the LunaNet architecture itself. So there are some limitations to this study. The study introduces the theoretical design of LunaNet. However, there wasn't really any empirical evidence to support these main ideas. So perhaps to improve this, they can introduce some form of simulation or evaluation methods that can provide this empirical evidence and can strongly support these main ideas. Another limitation was that the study didn't explain any sort of way of access to the LunaNet infrastructure for the average terrestrial user. So maybe they might want to consider incorporating or evolving the network design by implementing the infrastructure that can allow average terrestrial users to communicate with users on the moon. Thank you for listening to my presentation.